Morning, guys. So we're just going to finish up a little bit of the reflection refraction stuff that we didn't quite get to yesterday. Just a recap here. This simulation here is on the website, so you can just play around with it a little bit here. What we have here is a laser pointer of some sort. We say in general light has a duality of nature. When light is thought of as particles, as little photons, as packets of energy, you can imagine this is just a stream of red light photons. And basically, we're shining that photon here. Right now, we're in a medium called air, where the index of refraction is just a 1. So basically, pretty much like vacuum, the light waves can travel through it exactly no problem. That's this particle nature here. We will be measuring angles relative to the normal. So in this case here, we're 0 degrees here relative to this boundary. That's the particle nature. And then we're actually going to analyze this using the wave nature of light. So that's sort of using this metaphorical, the oscillating up, down, the positive, negative, transferring energy. Remember, we had said all these bright lines here are the crests, are the tops of the waves. Every time it drops to the trough, which is the darker band of the wave here, we're going to watch what happens to these bands here as they interact with the surface. Yesterday, we started taking a look at reflection. Reflection means whatever angle that I come in at. Let's say I'm coming in, I think last day when we tried it was about 48 degrees or so. The outgoing angle, we call it the reflected ray, because that's the ray when we bounce off this shiny surface. Even though water is not perfectly shiny, right? It's not like a mirror or anything, most of the light actually gets through. There will be a little bit inevitably that gets reflected off. And what we saw with the law of reflection was the angle that I go in at is actually the angle that I leave at. We're going to see today for refraction, especially with this sort of wave-like nature, because it's easier and faster to travel through the air, and we actually need to slow down in the water, we actually end up turning. We actually end up bending. In this case here, in general, when we go from an easy medium, a lower end value to a higher end value, we notice that the angle itself is larger coming in. We actually bend, we say, towards the normal. If I were doing this oppositely, if I put the laser pointer here and I try to shine it out here, as I get to an easier medium, I can walk faster, and as I walk faster here, I'm going to actually bend away from the normal. So either you bend closer to the normal, or either you bend away from the normal. In this case here, how do we explain this here is we actually use this marching band analogy. Imagine with the wave nature here, the waves themselves are just oscillating up and down. They're just doing that sort of sinusoidal shape there. We're watching these bright bands here. Remember, the beat, the frequency is set by the laser. No matter if I'm in the air or in the water here, the beat, the frequency will still be the same. We saw an example of that in the previous lesson. What I want to show you here is if you imagine these bright lines here are actually lines of a marching band, you're going to see that because I'm coming in on an angle, earlier, last day, I was just coming in straight like this. Earlier, in this case here, if I'm marching on straight and I'm at 0 degrees relative to the normal, my entire row of marching band people will actually all slow down at the same speed. So in this case here, they're walking fast, walking fast, walking fast, walking fast. They all hit the boundary at the same instant. They realize this index is more optically dense. It's harder to travel through. We're actually going to be traveling later on at a slower speed. It's more interesting when I come in at an angle, though. As I come in at an angle, maybe I can dramatize a little bit here. My rows of the marching band here are still walking along, but because I'm coming on at an angle, the closer side of the laser will actually encounter the boundary before the other parts. So what's going to happen is if you're on this side of the marching band, you've already hit the boundary, you already know you're going to start slowing down, and you're going to start walking a little bit slower, although trying to keep the same beat. The other guys on the sort of far side of this laser here, they haven't realized that we're actually going to hit a boundary yet. And because we're not realizing that, these guys here just, hopefully you can see it, these guys here just travel at the same speed. So on the one side here, they're slowing down. They're still marching away at the same beat. Their feet are still keeping that rhythm there, but they're not actually managing to walk as far away. Whereas the other side, which haven't seen the boundary yet, they actually walk quite a bit faster, just the same speed as they did before. If you've ever seen marching bands do this, this would actually be how marching bands actually turn and actually change direction, and it's exactly what this light model is doing. This side that sees the boundary first slows down first. They keep the same beat with their feet, but they don't walk as far. The other guys that are on the far side here keep walking the same speed, and eventually when they also hit the boundary, they also slow down. If they're going to keep the same beat and they're going to all walk at the same rows again, they're going to happen to have bent. So in this case here, you're going to notice we have the incident rate. Incident means oncoming. That's my incident angle. And you notice by the time that I bent, I'm actually going to be closer to the normal. So that's the marching band analogy I want you to keep as we do this using something called Snell's Law here. For reflection, we had no difference. The incident angle was equal to the reflected, but in this case here, incident and refracted will be different. So if you can pull out your notebooks here, we're just going to summarize a little bit of this here in terms of what's called Snell's Law. Right? So we'll just do this by way of example here. We have our, let's say, our water boundary. Let's keep it flat just for simplicity. This is our normal line. Our normal is going to be perpendicular to the surface. In this case here, it's going to be straight up and down, perpendicular. And what I'm going to do here is I'm going to shine in the light. Again, this ray here is going to be called the incident ray because incident means oncoming. It's coming inwards. The angle that I shine in at is going to be incident angle, or just theta I or theta 1 if you like, angle of incidence. This time, instead of talking about reflection, which I know is to be the same, using that marching band analogy here, I just want to make sure you have in your notebook here, using that marching band analogy, just make a note to yourself, one side slows down first. Right? The other side doesn't realize yet, the other side here, so this side here has slowed down a little bit here, the other side still travels really quickly, really fast. They slow down really quickly, really fast, and eventually they're going to have the same beat, but they're going to now travel off at some different angle than before. This light ray here, instead of being called the reflected ray, this is now called the refracted ray, because this ray here has undergone refraction, it has gone through. And therefore, when I do the angle here, I can call that the angle of refraction, theta r, or the refracted angle, angle of refraction. So let me just give you Snell's law, which will give you the relationship between the two of these here. Snell's law says for us, you actually have this on your formula sheet as well, fairly simple formula. It says n1 sine theta 1 is equal to n2 sine theta 2. And I'm just using sort of 1 and 2 just to indicate 1 is our starting medium, 2 is our later medium. You can call it ni theta I, nr theta r if you like. Just be careful you know where you're starting and where you're ending. So in this case here, like in the demo, we started off with n1, which was air, so 1.00, sure, let's put in that 0.003 there for air. And my n2, I'm entering a medium that's a little bit harder to travel through. For water, also on your formula sheet here, the index is going to be 1.33. So recap from last day here, we know the second medium here is harder to travel through. So harder to move through water, okay? So harder to move through, we indicate it's a slower velocity. And we saw in the simulation here, if one side actually happens to slow down first, while the other part doesn't know yet, slows down, doesn't know yet, slows down, doesn't know yet, we're going to actually end up bending towards the normal. So anytime we go from easy to hard, we're actually going to bend towards the normal. Let's verify that with our formula. Let me just give you some angles here. Let's say the angle came in at 30 degrees. So what I'm going to do is I'm going to say air has an index of 1.003. Let's say I gave you, I'm looking at 30 degrees, right? I could look at any angle. I could look at 40, I can look at 50. But Snell's law actually gives you the relationship. When you're now in a median that's now 1.33, when I actually bend, I'm expecting it to bend towards the normal. Let's just crunch through the math here. Make sure you are in degree mode again, 1.003. Let's multiply it by sine of 30. This gives me some random decimal, 0.5015. That's equal to 1.33 sine of theta 2. Do some algebra here, divide the 1.33 over. I probably wouldn't show that middle step there, so, 0.377. And then this time what I need to do is I need to find the sine, I need to find theta again. I need to undo the sine. So if you can go shift sine or inverse sine, arc sine, you inverse sine, and therefore I'm expecting something less than 30 when making sure you're in degree mode here, inverse sine of that decimal here, lo and behold, 22 degrees. So if I did this using the ray model here, our Snell's law actually gives us a nice relationship. If I send in something that's at 30 degrees, instead of leaving also 30 degrees, it actually bends towards the normal. It goes closer to this normal and actually goes closer then. So this one actually becomes that 22 degrees that we saw earlier. This actually gives, in the olden days when they did a lot of spearfishing, people some problems, because what would happen here is you might be standing in a sort of shallow bed of water here. You might see a fish that's actually in front of you. our brains are a little bit, they get confused because it always thinks light travels in straight lines. So if you actually see a fish at 30 degrees, you think the fish is actually directly in front of you, and yet the real fish is actually a little bit closer than you think, and that's because light travels a little bit slower through the water than through the air. When the sunlight shines on the fish, that same ray from the fish, the image from the fish actually comes upwards. It actually bends towards your eye at 30 degrees. It's our brains that naturally just think this is our sort of artificial fish. There is actually no fish there. So if you were to actually do this, if you were spearfishing or whatever, wherever you see the fish, especially the deeper the water gets, you want to aim a little bit closer because the fish is actually a little bit closer because the angle has bent towards the normal. And this is perfectly fine for all Snell's Law kind of questions here. Let's do one more practice. Let's say I'm starting up here. I'm going to send in an angle at a more maximum angle. Let's send it in at 80 degrees. Again, these angles here are measured relative to the normal. Although realistically what's happening is the sun's rays are actually striking. Sure, let's do that fish analogy again. The sun's rays are actually coming off the fish. The rays themselves are actually coming up towards you. It might be easier to think like you're an X-Men, you're like Cyclops, and you can send a laser beam. It's the same relationship anyways. So this time what I'm going to do, I'm going to still use air. Conventionally, we just use air as 1.00, so I just want to get used to that. And let me say this time the fish is actually at 30 degrees, but this time I'm in some liquid where I actually don't know the medium. It's actually some N question mark. It could be water that has dissolved many other solutes and whatever. Whatever you can do to the liquid might actually change the optical density. Now looking at these numbers here, I notice that my incident angle, my looking angle of 80 degrees here is larger than what it's kind of going through at. I would expect this one here to be the easier medium. I'd expect this one here still to be the harder medium. That's why we bend towards the normal. So in that situation here, make a note to yourself, I bend towards the normal. But nonetheless here, this is just an application of Snell's Law. This formula here should seem very easy to you here. We're just going to use n1 sine theta 1, n2 sine theta 2. I'm starting out in the air. This time I'm using 1.00. Sine of 80 that I'm looking at, I don't know what my n2 is, but because I know the angle leaving, I can go sine of 30. It should be fairly easy to calculate here. Sine of 80 was 0.985, give or take some rounding. Sine 30 is 0.5, so 0.5 n2. And therefore my medium, I just made up these numbers here, 0.985 divided by 0.5. I'm getting a medium of 1.9, so give or take almost 2.0. Just like coefficient of friction, this number doesn't get to be very large. That's actually already pushing it. Okay, so this index here is actually maybe something that's really optically rich and it's really, really hard to travel through. Just a quick little aside before we finish off this Snell's Law stuff here. From Snell's Law, we actually get our law of reflection. If you imagine, so just a quick aside here. If you imagine for the reflection case, we had been picturing this one here was a nice shiny surface. Maybe it's a shiny coating of the water, or maybe it really is a mirror. We said last day that your incident angle, as measured from the normal, theta I, here's the incident ray, theta I is equal to theta R. We said that was equal. We can actually verify that using Snell's Law, quite simply here, n1 sine theta 1 equals n2 sine theta 2. Because this time the mirror is perfectly shiny, and because this time we bounce backwards, this time our ends stay the same. If we were in air before, we're still in air afterwards. The ends end up canceling out. If you inverse sine on both sides, the sines end up canceling out, and therefore we get our relationship back, theta 1 equals theta 2. The angle that you leave at has to match up with the angle that you go in at. So because, yes, Snell's Law is much more useful when we actually go through, when we're actually bending either away or towards the normal here. When we're in reflection, I actually stay in the same medium. Reflection keeps us in the same medium. So therefore, the ends are the same, and therefore everything else cancels out. Right? So that's basically our lesson here. I'm just going to do a quick spin-off of the problem where Snell's Law kind of fails us, or we'll talk about what's happening here. So what's happening? Let's go the other way. So far, I've done a few examples of us going from an easy medium like air to something that's harder. Sure, I can play around with the unknown. I can play around with the unknown of what's the angle that it gets through at, or what's the index, if I know the angle that it gets through at. This time, I want to flip the scenario around. I know the simulation won't let me do this, but I'll show you how we're going to do it later on. Imagine this time I sink to the bottom of a pool of some sort. And what I do here, again, realistically, the light ray is actually traveling the opposite way. But just for simplicity, let's be Cyclops again. Let's send in a laser beam here. And let's say this is making an angle of 20 degrees. Let's just remind ourselves here, we're in water. Water's optical density, its refractive index is 1.33. That's the name of this value here. And let's just try to look up, out from under the water here, where the n is equal back to 1. This time what we're doing is we're going from a hard medium to an easy medium. We'd expect the opposite. We'd expect this marching band here to at first have a really hard time going through the water. Which side of the marching band actually hits the boundary first? This time it's going to be the left-hand side. And what's going to happen here is, although most of the marching band hasn't left the surface yet, this part here which has passed the boundary, oh, they're like, sweet, I can walk a little bit faster. Then a little bit later, this side here hasn't reached the boundary yet. There's a bunch more people that have now reached the boundary. They can walk a little bit faster. They can walk a little bit faster. And hopefully you get this idea here. As they start walking a little bit faster, they're going to end up, sorry about that, they're going to end up leaving at an angle that's actually farther away from the normal. If I actually compare this ray, this marching band as they leave, I would expect the angle out to actually be away from the normal because it's actually easier. I actually have a faster speed out here, faster velocity. So anytime I go hard to easy, I expect the angle to bend away from normal. Let's verify that using the Snell's Law, bend away from normal. So it's the same law. So n1 sine theta 1 equals n2 sine theta 2. And let's just plug it in. This time I'm starting in the water, so I'm 1.33. Sine of the 20 degrees I'm looking at. Sometimes annoyingly they give you the other angle. They say, oh, at 70 degrees from the surface, make sure you do the angle relative to the normal. That's the angle that you put in for Snell's Law. We're going to then enter easier medium with n equals 1, and then sine of theta r. Let's solve our way. What's theta r here? So 1.33 sine of 20 is going to be 0.45. That's sine of my angle, so I need to inverse sine that. Inverse sine of the whole decimal here, this gives me 27 degrees. I was 20 degrees in, and I'm now 27 degrees out. No problem. Again, there is this sort of bending. Our brains trick us a little bit. It always forgets about this refraction. It thinks whatever that we see, whatever objects over here, maybe your friend is standing over here, it thinks your friend is actually standing a little bit closer. I'm going to do exactly this example, and I'm going to show you Snell's Law complaining. So all I'm going to change here is I'm still at the bottom of this pool. I don't know why you're doing this, but I'm still at the bottom of this pool. But this time what I'm going to do is I'm going to look at some really extreme angle. So let me be looking at an angle of, let's say, 70. Not the 20 or the 30s I'm looking. I'm going to look at 70 from the normal. Same thing what I expect to happen. Water starts off from an index of 1.33. The air here has an index n equals 1.00. I'd expect it to bend away from the normal. Same question. I want to know at what angle does this leave at? What's the theta 2 in this question? This looks exactly the same as earlier. So let's use Snell's Law. n1 sine theta 1 equals n2 sine theta 2. n1, again, I'm starting in the water, 1.33. Sine of 70 is supposed to equal to 1, sine of the angle that it leaves at. This time 1.33 sine 70 gives you 1.25. That again is sine of the angle. Those of you that have done graphs of sine, you'll know that this is going to give you an error. When you try to do inverse a sine of 1.25, the sine function only goes between -1 and 1. It can't actually give you 1.25. Let's verify that inverse sine. Calculator gives you error. Right? If you haven't been sure up to this point, you can just say physics is broken. I thought this is the law. I thought this is supposed to give you how the angle leaves at. It is true. This is supposed to be leaving. But if you imagine here what's happening, every time I go from a hard medium to easy medium, I actually bend away from the normal. There will be some special angle that when I try to look out, basically the refracted ray, when it bends away from you, it's actually bending so far away from the normal that it's actually bending just along the surface. That's the maximum light ray. That's sort of when the outside hits 90 degrees, I'm going to be looking at something that's less than 90. That's the maximum I can do to actually look out at. If I imagine in this example, because I'm looking at some way extreme angle, in fact, the light ray has bent so far away from the normal, it doesn't actually leave the surface, it actually bends back the way it came. the name for that special angle, we're going to call it the critical angle. And basically, we're going to rationalize, well, what's happening in this error here. So let's find here, so part B of the question here, I want you to determine what's referred to as the critical angle. And let me just define that here, theta c. This is the maximum angle that the light ray just makes it out. I know it would bend away from normal, bend away from normal. Basically, when it's bending 90 degrees from the normal, here's the picture that I'm looking at. So I want to send in a light ray at some special angle, theta c, so that when my refracted ray, when this light ray here leaves, it's bent so far away from the normal that it's just making its way out, that it's just eking along the surface. So therefore, the theta 2 is going to be 90. Let's try this out here. Again, I'm starting from index of 1.33 over to index of 1.00. N1 sine theta 1 equals N2 sine theta 2. 1.33 sine of some critical angle. This time I don't know what I'm looking at. This is going to equal to 1.00 sine of theta c. Theta c is equal to 90. You can try that for yourself here. Sine of 90 actually equals 1, so this whole term just becomes 1. Sine of theta c is equal to this 1 over 1.33, and therefore theta c is the inverse sine of 1 over 1.33. So let's try that calculation out here. Inverse sine of 1 over 1.33, this gives me here, the angle is 49 degrees, give or take. So for a water-air boundary, going from 1.33 to 1.0, when you look out at some 49 degrees, the refracted ray is bending so far away from the normal, it's bending so far past the 0 degree mark, that it basically is just managing to eke out along the surface. Back to our earlier question here, why is it giving an error then? Well, earlier I was looking at 7 degrees. I was looking for an even more dramatic angle. And when I look at an even more dramatic angle, same thing is going to happen. The marching band here is going to speed up. But that time, because we're beyond the critical angle, we don't actually escape at all. We don't actually get out into the air. We don't even eke along the surface. What ends up happening is a phenomenon called total internal reflection. This is when the water was supposed to be a translucent medium. It was supposed to be a clear medium. It was supposed to let light rays through. It now sort of acts, when that angle gets to be too big, that light ray ends up just coming back down the way it came. So back to flesh out our example there is when we were looking at, earlier I was saying 70 degrees, our light ray here doesn't manage to actually leave at all. We're past the critical angle. It actually does something called total internal reflection. Total internal reflection. Okay. And I'll just emphasize here, when your theta I, when the angle you're trying to look out at is bigger than the critical angle, then that special angle which the light ray just managed to eke along the surface, that's the last remaining ray that might make it out. The water becomes like a mirror. And here's the wording here. Total means completely. So all of the light intensity here, none of the light actually gets out, not even a trace of it. But it's going to be internal and completely internal reflects. Okay. Reflects the ray back into the water. So anytime your calculators give you this error, it's only for going from hard to easy. It's only for going a big N to a small n. We don't have a problem going from a small n to a big N because I can bend closer to the normal all I want. I can even bend along the normal. That gets through. But if I ever go from hard to easy, that's a nice hint when you're trying to do critical angle. We always want to go from the difficult media to the harder media. We're going to get reflection instead. And we already did for Snell's law. For reflection, because I stay in the same media, whatever angle I'm looking at is 70, so it's going to leave at 70. If I look at 80, it's going to leave at 80. If I look at 60, it's going to leave at 60. That's just going to be angle in equals angle out. So hopefully that fleshes out a little bit more for you for Snell's law. There'll be some practice questions on the website there, and you can ask me any questions if you have any problems. Thanks, guys. Take care.